Hello. 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 Hello.
Yeah.
Get started. The screen itself. Okay, so let's get started. So before I get into the topics, which is word2vec, which we left last time, and today we're going to talk about RNNs. Before that, some logistical questions. So let's actually look at where we are. So yeah, so we are lecture number 5. So today we'll be talking about sequential models. Basically, if you've done time series, then we'll at least make some connection to that and maybe add comments or discussion if you have looked at time series models using some other packages or other approaches, then it's going to be relevant to what we talk today. So it's about 2 weeks from now that you'll submit assignment 2. Okay, so we'll talk briefly about assignment 2. If you have not started looking into it, it's a good it's good to start it early because it really needs some exposure to the underlying package that we'll use, not underlying, but the associated package that we'll use, which is PyTorch, right? So it's very similar to the first time you learned how to use NumPy or Pandas. Okay, so there's going to be that learning curve, and so it's important to get started early, especially the question 1 of assignment 2, and also use, if you can, and ideally you should be using PyTorch to also solve part 2 of assignment 2. Okay. So let's talk about assignment 2 in a second. So that's where we are. And about 4 weeks from now is a little bit less than 4 weeks is the meeting as well as the submission of a project intermediate report. Okay. So the earlier you start, the more ambitious or more time and bandwidth you can spend on these things. So this is a big component of the course, as you saw in the grading section. So start thinking about what you want to do for your project. The best way is if you want to enter some domain, maybe after this program, or you have some domain expertise, kind of relying on that would be good, because then some extra knowledge that's not there if you just download data set from Kaggle, for example. Okay, so start thinking about it and reach out to myself or the TA, and we've seen several projects over the past several years actually, so we can tell you when the project is maybe too difficult, out of scope, or maybe need some more extra thinking and so on. Okay, so you want to keep us in the loop. Actually, since the project is a huge component, there's actually 2 checkpoints to really ensure that you have your code running, you're not facing computational issues, you're not facing handling large data set issues, you're able to achieve something, tangible, okay, by the end of the session, end of the course. Okay, so that's a quick thing about that. So let me now talk about assignment. Any questions about project before I get to the assignment, and then we'll come back to goals for today and so on. Okay, so people have not yet looked at assignment, it looks like. Yeah. So how many of you have actually read the assignment question yet? Yet to read it? Yet to read it? Okay, so maybe I'll kind of not go over it today. Let's see how, I strongly suggest looking at it. Okay, so it'll be very similar pattern to other supervised learning problems and so on that you've done in other assignments in other classes. But of course, each question has its own, thing that you want to try out and so on. So for first part, look at the assignment and look at the example script that we have in the examples folder. Right here, the CNN has a CNN classifier example. It lays out an example way in which you can instantiate the torch packages, torch vision, from which you can get the pre-trained model, ResNet 18, and so on. So it shows you the full thing. So you can run it, for example, in Colab. You just need to ensure that Google Drive is mounted, and then you can pass on the data set. Okay, this particular example is of trying to classify between ants versus bees. So you just need to ensure that this data set here can be downloaded and is set such that you can access it from some location. You just need to change the notebook such that you can mount your Google Drive and change the path here. Okay, and then try to see what's happening in each of the cells. It's important to there's going to be there are parts of the assignment which also involve, sorry, where is it? There's parts of the assignments which also involve like, for example, displaying correct predictions, incorrect predictions. There's some logic involved. Okay? It's not exactly training the model, because training the model has a standardized script, and we are, in fact, for this question, half the question is about not training a model as such. There is a training of the model involved, but if you think of feature extraction version of transfer learning, then much of the network is not getting trained. It's just the last layer which is getting trained. Fine tuning, if you think about it, it's mostly the network is already fixed. Most of the weights are already fixed. You're kind of slightly changing the weights, right? So training is not complicated for this, given that we have the example. So, but there are some helper things that you may want to write. For them, you may have to write your own helper functions. Okay, so that's where I think understanding, it's not complicated. There are some objects that we use in the notebook, like you can just look at imports, right? So we are importing something called data sets, something called transforms. We are yeah, and also using things like data loader. So those are things that if you learn once, you will kind of use the same concepts in other, maybe if it's not related to images, you'll still use the same ideas. Okay, so you can even use it for tabular data, actually, data loaders and so on. You can define your own data loader for tabular data, but those are steps for which you need to take the initial step, which is to understand what's going on in this notebook. Okay. And also the big delta will be using torch to actually train. In assignment 1, you use Keras, and Keras is great. You also saw an existing explicitly written gradient descent loop, right, where you're doing weight updates. The torch, the big bang per buck with torch or TensorFlow or MXNet or one of these many of these autograd capable packages is that they do it for you. And so there's a particular pattern in which you're gonna use a gradient descent approach, okay, technique, right? In fact, in this, you basically just do this, right? So these are the 2 steps which do magically for you a gradient computation, like dot backward does the backprop from loss all the way to gradient with respect to gradient of parameters with respect to the loss. Gradient of the loss with respect to the parameters. That's magically happening with just this one call. So loss is the final thing given the parameters in the data that you're computing, and then you can get the gradients with the step. And then the actual weight update step is just optimizer step. It's just W new is equal to W old minus some learning rate times gradient values, right? So it's not exactly that. Depends on which optimizer you use, but These are all gradient based approaches. So kind of variations on the gradient descent idea we saw in lecture 1. But to get here, you see a lot of code, right? So to just do this main step on a predefined model, pretty much, this ResNet 18, you have to do a lot of setting up of the whole problem. So just go through this. That will make life super easy with question 1. I strongly suggest, especially groups, each one should try it individually. Okay, so that's where you learn the most. That's the ambitious part. I mean, I wouldn't say ambitious, but do it individually and try to collate your discuss and see where the hurdles are, and then maybe submit your assignment. That will be really helpful, especially if you're really this is an elective course. You are here to really experience deep learning. So trying it out and hitting errors and then debugging them is the way to go. And the second question is a non-standard question. It's where you need to understand the problem. It's like how most of the challenge is just to understand the problem. The actual it's related to recommendation systems, and if you understand the problem and then think about what gaps are there with respect to what you know and what needs to be written in code, then you'll be able to make progress. Okay, so here I say or TensorFlow, but it's up to you. Okay, so but majority in the class we kind of have torch based examples. So if you want to prefer torch, that's fine. Okay, so I think maybe in a week or two, when you guys are actually almost to the deadline, maybe we can again discuss in case you're facing any issues with assignments. Okay, so last comment I want to say is that you see the word embeddings here. So it's actually related to word embeddings. So very similar idea. So today, in fact, right after this, we'll talk about today's goals. And the first part is about, again, just recapping word embeddings and looking at word to vec. So embeddings for movies just mean we want to get a vector for a movie. Right? Movie is an abstract object. I mean, movie, if you really think about it, there's actually a finished product, which is the actual footage. And there's a lot of things in the footage itself, as well as metadata around it. All letters can be abstracted out, and you have that one vector for a movie. Okay, and so if all movies have such vectors, you can talk about movie relationships, and that's how you can make recommendations. Okay, so that's one way to do it. And so we are really using the embedding idea. Okay, so this representation of objects which are not just numbers or columns already. Okay. Okay, let's come to goals then. Any questions about this? So far, I've only been talking about logistics. Any questions about the difficulty of the course or anything that we covered last time? I do have to say that for some of you, this may be one of the more difficult courses, but that's part of the experience. Hopefully, it's just a starting point for you to be get more and more familiar with deep learning. Okay, so if some of you are thinking that the course is super difficult, we'll try to keep things simple and easy. But so if you find something not clear, immediately ask. Okay, so we can repeat it and tease it out so that it's clear. Because some of the things that we're seeing here, they're all related to exactly the things that you've seen in 575 and 572. It's just that if you're not able to immediately make the connection, we can make the connection so that it becomes a little bit easy to digest. Okay. So let me come back to then what the objective is. So we are focused on lecture 5 or module 5, but we want to cover one which we did not cover last time, which is word to vec, which is a specific version of this auxiliary prediction problem. Suggested, built by some folks at Google almost 9 years ago. So we look at their specific version of the prediction problem, and eventually they were able to build these word representations of word embeddings, and they let anybody download it and use them. Okay, so we'll see what exactly was the way they were constructed these word vectors. But much of today's objective is actually the second part, which is know when prediction problems can be solved using, can have sequential dependencies. So many times you may have the missing, feature problem where your prediction doesn't just depend on the data that you have observed now, but may also depend on what happened before or the context. Okay, so that's like expanding the feature space essentially. And that's what's going on with all these sequential dependencies or these time series types of problems. You want to know what happened before to say what could happen next, and not just the information that you have now. Okay. So we'll look at so today's today for this part, we'll mostly, it's not a difficult topic. There are a lot of variations, but we're looking at only the popular neural network definitions or model definitions, architectures. So we look at the vanilla RNN architecture and something called unfolding. It's just a simple concept of how to draw the diagram. Okay, very similar to drawing the feed-forward neural networks. And a popular, I guess, variation of RNN, which was suggested, in the 90s and kind of took off and does really well empirically. So it's called LSTM. So we'll look at its details. Okay, so it's going to be mostly about the details. And remember, so far we have looked at feed-forward convolutional neural networks and word embeddings, which we'll see today. Mostly we've been discussing about the forward pass. Okay, that's where the understanding of, hey, given the input, how is it being massaged to get to the scores? Okay, that's the perspective we'll take first, because once you can define the forward pass, the software like PyTorch can just do the backward or something and get you the gradients, and so they can update the parameters. Okay? So it's all about the understanding the forward pass nicely. And so today we're going to exercise in like a lot of details on LSTM, but hopefully we'll not get lost in the details, but kind of abstract out and say, hey, we're just doing a forward pass. There's some interpretation of the architecture, and we'll look at that. Okay. And throughout the lecture, there's going to be some connections to, hey, what are these models, or say what are the application use cases basically beyond just time series models. Okay, the time series predictions which we might have seen in other courses. Okay. So it's essentially related to time series, but it can capture more, okay, especially with unstructured data. So that's the goal. Any questions here? What the yeah?
Is this the same LSTM model that is usually used in stock model?
Yeah, you can do stock price prediction using LSTMs. Yes, or stock market or crypto market or any for weather prediction. Yeah. So wherever you're using vector auto regression or any of these ARIMA or those types of models, if you have heard of them, you can use LSTMs there as well. Yeah. Okay, so let's actually jump over to. So I'm using this slide first, but we'll go over to where we want to talk about word to vec. Actually, let me go back to a couple of slides before this. Yeah. So the core idea is not complicated. So what we want is, instead of one-hot representation of words, right? So we can just say word present or not. What we want is a vector representation for the word, right? So one-hot encoding is just saying, hey, if I have a vocabulary size of 10,000, then I just need for each word a 10,000 dimensional vector, where that coordinate for the vector will be 1 if the word is present. If not, it's not present. Okay. So, but why 10,000 vector? Why not just one feature? It's just it's the same thing. Okay. I'm just talking about, if you had, let's say, 100 words in an email, you would have this 10,000 dimensional vector where each location where the word is present will be 1 and everything else will be 0. That's the one-hot uncoded representation of the representation of the whole input text, right? So here what we want is something beyond that, and in particular what we want is vector representations, and we're going to base it on the following idea that words that appear in same context or similar context share semantic meaning, and we want to capture semantic meaning. Okay, so we want to capture semantic meaning. Words that appear in similar contexts, we hypothesize that they have they have shared semantic meaning or similar semantic meaning. And so now let's use this words appearing in similar context to kind of bias, kind of direct us to how to represent these words. Okay. So there are a couple of ways. One of them, which we not discussed in this lecture, last lecture, is count based, where you can just say, hey, let's make a matrix, word cross word matrix. So very similar to item cross item type of thing. Think of a word cross word matrix. So you can just say, hey, for each word pair, how often do you think they they appear in similar contexts? Basically, that number in that matrix should just say, hey, word cat and word dog, do they appear in similar context? Some score like that. Okay, so count based just means just look at all your text, look at the word cat, which sentence did it appear? Okay, and look at the word dog, which sentence did it appear? Do those sentences look similar? If they look enough similar, then increment the count. If they don't, then keep it others. So that way you can have some counts where higher counts means maybe those words appear in similar contexts. Okay, so if you have that matrix, then you can do dimensional reduction. Okay, by doing dimensional reduction on this count matrix, you kind of get these word representations by default. Okay, so basically what does dimensional reduction do here is just you have original square matrix. You are saying that square matrix is actually low rank. Okay, low rank just means if it's a 10,000 cross 10,000 matrix, you're saying, hey, the rank is only 300. Okay, that means that original 10,000 cross 10,000 matrix should be a product of a 10,000 cross 300 matrix times 300 cross 10,000 matrix. Okay, so it's like a tall matrix times a wide matrix. Okay, and that's what PCA does. Okay, so that's what PCA / SVD they just do. They just compute eigenvalues and eigenvectors in the process, but eventually you can get these tall vector and a wide vector. And the tall vector you can think of, hey, I have one row per word and I have a 300 numbers per word. I can just call them the word vector representations for the word. Okay. And you will see a similar idea today. But so that's count based idea, and you can do that. But the other approach is to kind of get these word representations by solving a intermediate prediction problem. Intermediate is an auxiliary prediction problem. We don't really care about that prediction problem. No, it's not a specific. It's not a prediction problem that was motivated by an application, but it's a prediction problem by which, if we solve the prediction problem, we, as a byproduct, will get the word embeddings. Okay, so and then we can kind of use those word embeddings elsewhere. So that's the idea. And yeah, and just to kind of reinforce, like what do we mean by word embeddings? Just think of word embedding is like represented by this function W or a matrix W. We are going to take both these views. Remember, matrix is also a function. A matrix represents a linear transformation, linear function. Okay, so we have this function. Given a word as an input, just think of a Python function where given a word as an input, spits out a vector, which is like let's say 300 dimensional. So that's this that's in 300 dimensional vector space. So something like this. If you pass universities, you get some vector. You pass class, you get some other vector. Okay. So that's the API. And so internally, this function could just have a matrix. Like, hey, if you send a word, that word may correspond to some index. Pick up the vector in that index and just return it. Okay, so in a sense, it can be just a matrix, like a lookup table, basically. Okay, so how do we get this good W, where hopefully the words are such that words that appear in similar contexts have similar vector representation, capture semantic meaning. So what do? We kind of initialize W or the original W matrix with some random vectors, and hopefully we change these random vectors, as in the entries of the vectors are just some numbers. Now these numbers themselves are parameters, and we kind of change these numbers, okay, such that we achieve something on a something meaningful for a task, okay, for a prediction task. So what we are learning is W has parameters. Basically, each entry in that matrix is a parameter, and you change the parameter such that you do well on the prediction task. Okay, so here's an example task, and we'll flip it over. But this task, the reason why I'm introducing this task is very similar to word2vec. So word2vec, by the way, we'll look at word2vec in 2 minutes. So word2vec has two versions of two approaches. One of the approaches is related to this, and that's why this was introduced here, because we'll not talk about that approach in detail. But let's see what the prediction task is. Let's get an intuition for, and this doesn't have to be. This just is a teaser to get a sense of, hey, here's a related prediction task. If we can solve it, we can get word vectors as a byproducts. Okay, so here's the task, which is you have the task is given 5 words, predict whether it's a valid sequence or it's not valid sequence. Okay, given 5 words, predict it's a valid sequence of words or whether it's an invalid sequence of words. So given a text corpus, we can create this data set. So we can just say, hey, look at the first 5 words and call it valid. Next, look at the next 5 words, let's call it valid, and so on. So at least the valid class we can easily create. The invalid class, we can take the 5 words and say, hey, let me replace the third word with some random word in the vocabulary, and let's call it an invalid pair, okay, where it's an invalid sequence and the label is invalid. So we have created from a text corpus, we have created this supervised data, right? And if you have the supervised data, then you can define a classifier where you're trying to use these word vectors. So remember, this W is, think of that as a matrix or a function which has parameters, okay, such that input is a word, output is a vector, right? So since there are, let's say, 5 words in, the sequence's length is 5. So given this 5-word length sequence, you either say valid or invalid, and hopefully you minimize the binary cross entropy loss. And of course, when you minimize that, the classifier itself may have some parameters. Let's say it's a linear classifier, it may have parameters. You kind of change those parameters such that you do well in the loss, but you also change the parameters of W. Now the question is, we have not really opened up W to say, hey, what does it look like? But the teaser is that W is just a matrix. Okay, so we'll look at word2vec in detail, and so we'll see what W looks like. But it's just a matrix. Okay, it's just being used multiple times. That doesn't change the fact that W has parameters, and so you can always compute the gradient of the loss with respect to W's parameters also, and change the parameters of W. Okay. So what exactly are parameters of W? In fact, the vector representation of the word, each entry itself is a parameter. Okay, so you can just think of that. Okay, so the point is that hopefully the classifier parameter will change so that classifier does well, but W parameters also change such that the classifier this classifier does well. Okay, so W is also as part of. So you can think of this whole thing, put it in a bigger box, and say, hey, given the sequence, I'm trying to predict a valid or invalid. It's a binary classification problem. Hopefully, I can change all the parameters of everything involved here such that I can do well in classification.
So what happens when the input size is different? So
in this in this version, we input size in the sense that the number of words.
Yeah.
So we have defined in the classification task that it has to be a fixed length. Okay. Here, and in word2vec also we do the same actually. In fact, word2vec, this type of a version of the problem for word2vec is called continuous bag of words representation, CBOW version of word2vec. I'll make a connection to this diagram all the way to the end, but now we're going to jump to word2vec in gory detail, so that in the sense that it's not complicated. By the way, word2vec neural network is actually just a one hidden layer neural network, a feed forward neural network. Okay, so we have seen one hidden layer neural network in the second lecture itself, but it's just the interpretation of what's going on to get word embeddings that's going to be new. But yeah, for your question, of course, we will keep the number of words fixed here. Okay? And we'll make a connection to this picture on slide 34 all the way to the end, at the end. Okay? Any other questions? Okay, so let's actually skip over all this. This was mostly a discussion about if you have already had a word embedding, then how would you kind of see whether it's interesting or not? And some people try to make sense of, hey, two words like man, so woman, the word vector for woman versus vector for man has some direction, and that direction is very similar to the direction of vector for aunt minus vector for uncle, and so on. So people did a lot of diagnostics, very similar to CNN diagnostics that we saw. And then there was some extensions of, if you could get word embeddings for a single language, like a single corpus, then you can also get you can also use it for a third-party task, and that's a major use case. Like if Google has already trained word2vec and they have the embeddings, you can use the embeddings as is for any other task where you don't want to do anything to do with NLP. That's fine, as long as you can map a word to the vector, pick up the vector that Google has provided, for example, you can always move forward. And there were some other extensions like, hey, you can also get two embeddings of two different language, two different vocabulary, and you can embed them into the same space, and it can be useful for like translation, like a very naive translation, and so on. So this part of the lecture notes was mostly about extensions to embedding. If you can do a single embedding of, as in like for a single language or single corpus, you can embed English words. You can also do something like embed English words and Chinese words into the same space. And I think there was extensions where you could embed not just words, but English words and images in the same space. These all require slightly different supervised learning data. So we didn't spend too much time on what the exact data sets needed for these are. But that was the motivation for these slides. Okay. So shared embeddings have their own uses. You can, for example, an unknown image, you can always get a word for it directly if you had a shared embedding like this. But let's actually directly get back to our word embeddings. How do we construct it, and how did Google construct it back in the day? Right? There are many versions that people have trained. Word2vec is one instantiation. There's another popular one called Glow. I think you may be using it for your assignment number 3. Okay. So in assignment 3, actually, you're going to do language translation. Okay, and we'll talk about going from English to French or something like that. So in that, you can use these embeddings. Okay, so so Globe, and then there's other implementations also. But Let's look at word2vec in detail. So as we recapped earlier, it's a predictive method. It falls under that, not count based, but it's going to construct a simple prediction task such that the byproduct there, which is word embeddings, is what is actually going to be used for in the future. Okay, so that's what we want. And so we want vector representation of words that capture their co-occurrence statistics, basically words which occur in similar contexts, have similar vector representations. So as I mentioned a couple of minutes ago, word2vector or word2vec has at least the original researchers, they developed two different prediction tasks. And the one which we're going to look at is called skip gram prediction task. And we'll talk about what is meant by skip and gram and so on. The illustrative example I showed earlier, it's that version of the predictive task is called continuous bag of words. Okay, and that's why, so we'll keep that part aside and make the connection towards the end. But let's really focus on skip gram, because that's actually just, as I was saying, is one hidden layer neural network. Okay, and in fact, one hidden layer with no nonlinearity. Just to give you a sense of like, why are they even deleting nonlinearity? That seems crazy, right? So, but we'll talk about this in detail. Okay, so what is the prediction task and what is the architecture? Okay, so we're gonna build. So there's gonna be a prediction task and there's gonna be a model to kind of do well on the prediction task. The model is gonna be a single hidden layer neural network. Okay, and in that single hidden layer neural network definition, we're gonna kind of interpret one part of it to be the W stuff, and other part to be the classifier stuff. And so we want the W stuff. Okay, so we're gonna interpret this architecture and pick up part which is gonna be W, related to W. Okay, but as I said, the goal is, from any of these types of tasks is just learn the weights of the network, which is, I mean, the goal is to learn the weights of the network, of course, because we want to do well on the prediction task. But this doing that classification task well and learning the weights of that network will give us W. Okay, so that's good. So what is the task? The task is now slightly different. Okay, so it's just like an example. The task is you pick a word, so it doesn't have to be middle of a sentence. You pick a word in a sentence. Okay, so forget about the word middle. Pick a word in a sentence, and you pick one of the nearby words. Nearby just means like words next to it or before it or after it. At random. Okay, maybe pick one of them, and then that word pair is going to be is an example of your training data. Is a data point in your training data. So that word pair with you picked one word, that's your input. You picked another nearby word, that's your output. Now your prediction task is to, given this input word, predict this nearby word. Okay, so in other sense, you want to say, given this input word, what is the probability of each word being this nearby word? Okay, so this output number of outputs is actually the vocabulary size now. Okay, let's say 10,000 or something. So input, I mean, here I'm saying it's a word pair, but it's actually just drop the pair part. So it's actually input is just a word. In fact, pair is confusing. It's not correct. Input is just a word. In fact, at this point, we don't have, since a word embedding. Let's just say if you have input word, we're just gonna one-hot encode it. Okay, for now, because right now, we have to start with something. We'll just one-hot encode it. One-hot encoding just means, as I said, it's just one at some location and everywhere else it's 0, right? And we'll see that example actually. An output is this going to be some scores. Normalized just means probabilities basically. And the number of scores, number of score coordinates will be the number of vocabulary, number of words that we have in our dictionary. So if it's 10,000, then there's going to be 10,000 numbers. Okay, they all have to sum up to 1. It's a multi-class classification problem. And what do you want? You want to ensure that the nearby word, at least in training data, whichever nearby word it was, the probability for that word is higher, hopefully high than any other word. Okay, so is the task kind of clear? Actually, we'll look at some example in the next slide. So nearby just means any word, like words which are +2, -2 next to this word. Those are nearby words. So here's an example actually. The next slide. So let's say you had this sentence. There's going to be lots of sentences in your corpus, but let's focus on one sentence. The quick brown fox jumps over the lazy dog. So here, now what we're doing with this sentence is we're creating lots of training examples. What are the training examples? Pick any word, let's say fox. Then I look at nearby words like quick and brown and jumps and over. And I'm going to create, for example, here I've created 4 examples. If you look at the bottom right, fox is the input, quick is the prediction. Quick should be the prediction. That's my training data. Fox is the input, brown should be the prediction. Fox is the input, jumps should be the prediction, and so on. Okay. So with the prediction part, as I said, the output is we're going to produce a score vector which is 10,000 dimensional, whatever vocabulary size, let's say 10,000. So prediction part just means the coordinate for quick, the probability should be high. Okay, so the output side, we don't have to worry about word representations. Input side, how do I pass fox as an input to the model? Okay, that's where I'm saying you can just think of fox as being one hot encoded, in the sense that again the input vector is going to be a 10,000 dimensional vector where the coordinate for fox will be 1, and that's the input to my model. Okay. Yeah. I mean, this is just word to word mapping. Yeah. There's some lot of details, like these details. Some of these will point towards the end. Okay. Like for example, there's actually in the Google's actual creation, they sometimes also created not individual words but pairs of words, like a phrase also as a kind of a word, and so on. So they don't exactly correspond to the English vocabulary, for example. Yeah. And not just English, these types of things have been done for most of the languages in the world. In fact, if there's some language that has not been done, that's a good project to work on. I mean, at this point, I think there's going to be very rare languages for which you don't have word representations, but for many many languages, folks have already created these types of vector representations. So we are only talking about English.
Professor, so in this sentence, if we hot and put the word quick,
yeah,
for example, so in the output we will get something like, let's take a word fast. So fast will have a high probability.
No, we want quick to have high probability.
Okay.
So for this example, the first example pair, if I pass D as input, I want out of the 10,000 probability numbers that I'm producing, I want the probability for quick to be the highest, so that my loss for that example is low.
What the final vector?
Final what?
The final vector, final output.
Yeah, the output of this model is just a 10,000 dimensional vector. It'll have one score for every word in the vocabulary. One score or normalized score just means the probability. You want the probability for quick to be the highest and everything else to be the lower than that. So that's how you just think of the output as like a multi-class classification problem where the number of classes is the number of words. So we just want the word for the coordinate for quick to have high score or higher probability than everything else. So actually we'll kind of maybe come back to this because we're going to spend 5 to 10 slides on this. Any other question here? So here we are just setting up the data. Okay, what is the data? Data is just input is a word, output is the word, and we want to predict given the input word a nearby word. So you can see that for the same input there could be multiple. Like first example is saying, hey, given D you should predict quick, but the second example is saying given D you should predict brown, right? So but it's not a conflict. Okay, you can have data where for the same feature vector you need to predict 2 different things. Okay, it's not an issue. Yeah. So let's give some example numbers. I mean, this is just for illustration purposes. Let's say we have 10,000 words in a vocabulary. And as I said, this is just talking about the input encoding. So let's say input is just going to be a 10,000 dimensional vector where the appropriate word has 1 and everywhere else it's 0. Okay. And in the example, for any data example, the output word is also represented as a 10,000 dimensional vector where one of the coordinates is going to be 1 and everything else is going to be 0. Okay. That representation is just for our understanding also. Okay, you don't have to create that 10,000 dimensional vector explicitly, but just for our understanding. So network, what it produces is 10,000 numbers, okay, scores or normalized scores or probabilities, and each coordinate is the probability that that word is the randomly selected nearby word. Okay, so that's what it's doing. So we'll take an example word pair and think about it in the next slide, but let's look at the network architecture. Okay, so the network architecture is as follows. So you have some input vector, okay, so 10,000 dimensional. So from here there's going to be one hidden layer, so it's a one hidden layer neural network. So there's going to be one set of neurons in the center, And there's going to be an output layer. Output layer is going to be 10,000 dimensional because that's that's our vocabulary size. And as this slide says, there is no non-linearity. Okay, so there's no non-linearity. So input vector is being transformed via the usual wx plus v that we saw in the first or second lecture to some intermediate number of neurons, and from that vector again wx plus v to get to output score vector. Okay, so clearly the second w should have, for example, the number of rows should be 10,000, so that it produces 10,000 dimensional output. Similarly, the first matrix here should have a 10,000 columns so that it can actually get multiplied with the input vector. Okay. Now this hidden layer, as I said, is no non-linearity. Then you may say, hey, what is the point? Then it's not, it's equivalent to literally a linear classifier. That's true, but there's a particular choice that we made here already, which is that we picked 300 neurons. Okay? It turns out that this number of neurons is the dimensionality of your word embedding. Okay, so as I was saying earlier, although the network is this, we're going to interpret a part of this to be W and a part of this to be actually related to the classifier. You can see that there are only two pairs of weights and biases, right? So there's a weights corresponding to going from input to hidden layer, and then there's a weights corresponding to going from hidden layer to the output. So we're going to call the weights going from input to hidden layer to be the word vector matrix. Okay, so the transformation going from input to hidden layers is exactly our word vector matrix, where each column or each row, depends on how interpreted, is going to be just a word vector representation. And then the remaining part is just a classifier related, so we're not worried about it. Okay. So is it clear? So this is the network. So the objective, as I said, is to maximize the normalized score or like probability or something like that of the correct nearby word. Okay. So if you think of the loss function, like let's say there are some keywords, then if every word has like a context window of size 2, which means that two words before, 2 words after, it's just all approximation, okay? Because if you're at the start of the sentence, you may not have 2 words to the left of you, right? Then you have almost like 40 times of training data, and then you would have a like you can take this objective, or you can also do so this is objective is saying for each word, sum over each word, sum over all the context window plus 2, -1, -2, and +1, +2, log of the probability of that word given the context, given the current word, right? So this is just this is exactly cross entropy loss. Okay, so this is exactly cross entropy loss. Okay, and it's summed over all the words and all the. So this double summation is just over all the 40 examples basically. So this is just to kind of say, hey, what is the objective? And so you want to kind of minimize this as a function of the parameters of the network. There are only 2 sets of parameters: the weights and bias of the first side, input to hidden, and then the weights and biases of the hidden to output. Okay. So this interpretation of the input to hidden, we're just going to do a little bit of massaging. Okay, this is just renaming variables, nothing else. Okay, rename the variables so that we can better interpret what the word vectors mean in that matrix. So let's say originally the input should be input to hidden. The weight matrix should, let's call it W naught. Okay, then what we're going to do is that W naught, remember, if that's the input, that's the weight matrix corresponding to the hidden layer, basically multiplying with the input, then that matrix should have 10,000 rows, sorry, 10,000 columns, because the input is a 10,000 dimensional one-hot encode vector, right? So we don't like 10,000 columns, so we're going to just transpose it. So let's transpose the output. So hidden, if you remember, hidden is equal to, so Wx is equal to hidden. Right? So Wx plus B actually is equal to hidden. So let's just transpose the operation, and let's call the transposed matrix W. Okay? So the transposed matrix is W, not the original matrix. Okay? So why transpose, we'll see. So what's happening is this W matrix has 10,000 rows and 300 columns. If it's directly thinking that's the network, the original matrix would have been 10,000 columns and 300 rows, because the number of neurons we have produced is number of neurons is 300. So the number of rows of the first matrix would have been 300. Instead of that, I want to make the number of columns of the first matrix to be 300. Okay, just transpose it. Okay, so this was the hidden layer weight matrix, or the weight matrix multiplying from input to hidden. So we transposed it. So there are 10,000 now. Therefore, there's 10,000 rows and 300 columns. We're just gonna interpret it row by row. So it's like each word corresponds to one row, and each row, which is the output of the which is the 300 neuronal output, we're going to just call it the features of the word, or basically the word representation. Okay, this is literally the word embedding. So we're going to interpret it from that one hidden layer neural network, that part to be the word embedding itself. Okay, so maybe this interpretation is a little bit confusing. Let's actually take an example. So in the next slide, so here, let's say we have a word for cat. Okay, so cat, we want to represent cat as a one-hot encoded vector. We know how to do it. We just yeah, so we just pick one location to be 1 and everything else to be 0. Okay, has some coordinate, right? Yeah, so if you multiply this one-hot encoded vector with W, what happens? So if you multiply this vector with W, all it's doing is select one row of this W. This is kind of straightforward. So let's look at it. So if you have this cat vector, so let's say the cat is the 4th coordinate. It's simplified here, so the number of words here is only 5. So let's say cat is the 4th word in the vocabulary. So if you multiply this cat vector with W, remember we just kind of define W to be the transpose version. So it has number of words as number of rows, and columns to be number of features. So we multiply this, and why are we this is like a transpose of the original input vector. Remember we did the transpose operation. So multiply this with this matrix. All this is saying is, hey, if your 4th coordinate is 1 and everything else is 0, just pick the 4th row. Okay, that's what's happening. So you can actually check that by multiplying this with this. You'll see that 10 is picked. Multiply again this with the 2nd column, you'll see 12 is picked, and so on. So that's kind of expected, right? So so when you pass in cat as input, you're just picking one row of your weight matrix. Okay, so that's like a lookup, right? So that's a given cat. This is the vector for the cat. Okay, and so that's pretty much how that's one of the reasons why we are interpreting the input side, the mapping from input to hidden layer, that weight matrix, or the transpose of that weight matrix, to be the word embedding matrix. Okay, so now let's look at what exactly so what exactly is the network doing, right? So in the sense that let's think of pair of words, and let's say they appear in similar don't appear in similar context, like for us, for now it's not super important. Let's say we pick a pair of words like ants and car. Okay, so what is happening in the forward pass of the network, right? All we're doing is that, let's say ants is the input, and there's no there may be corresponding nearby word for ants, but let's say it's car, or maybe it's not car, doesn't matter. So we pick the word vector for ants, which is the 300-dimensional vector in the first part of the layer, right? And then it's getting multiplied with it's getting multiplied with a weight matrix, which produces 10,000 scores. Let's say if you focus on one of the outputs that is producing, let's say car's probability, then that output is only corresponding to multiplication of this ants vector with a column, with a column which is with a so with a column which is with a row of the output matrix which is 300 dimensional. Okay, so it's just, so what I'm trying to say is that one number, for let's say if you want to focus on one coordinate of the output, let's say car, that output is kind of influenced by the input word vector for ants times a vector for that output word itself. Okay, so so why are we kind of explaining this in detail is that you want to kind of intuit why the prediction task helps us get word representations where words which appear in similar contexts have similar word vectors, because we still have to kind of justify that. Okay. So let's actually justify that, in fact, right now. So if two different words have similar contexts, then similar words will appear around them. Okay, so if cat and dog, for example, they may have similar words around them compared to a cat versus an airplane. Okay, if similar words around appear around them, then the output probability vector should look similar. In the sense that if you think of passing cat as an input, the types of words that are nearby to cat, you want to try to make them ones, right? You want to train the model such that the output probability vector, so the scores for those nearby words are high. Now, if you pass in dog, you'll have some probability vector where the scores for the nearby words are high. But we just said dog and cats may have similar nearby words, so this output probability vector, in general, should be similar to these two words. Sorry, similar for these two words. But if output vectors have to be the same, then the only thing you can do is to make the input the word vector same. So why is that? Because there's no nonlinearity, and on the input side, cat and dog have different representations. In fact, they have different coordinates 1. Okay, so you cannot change that, but the output vectors have to be the same, and it's a linear transformation essentially. So you have to change the word vectors for the two words. Okay, so that's just kind of reverse engineer. Like, it's a very simple network. So if outputs have to be the same, inputs are different, there has to be something in the network that has to change, right? That has to accommodate so that you get similar outputs. So that's how you get cat and dog to have similar vectors compared to cat and, let's say, airplane. Yeah, so this slide is not saying much. So in general, that we are capturing that co-occurrence statistics that we just discussed. For example, words like university and masters would appear in similar context and similar word vectors. You also have, they don't have to be cat and dog. Like, it cannot be it may not be synonyms. It may not be. I mean, for example, antonyms could have similar word vectors as well. And we also handle like other issues like car and cars. Two different words with one is plural of the other can also have similar word vectors. You don't have to be very careful. Okay.
So what did you explain? One Hamming distance.
So one Hamming distance is the Hamming distance is for two vectors. Hamming distance is the number of places where it's different. Okay. Number of places one vector is different from the other. So if your vector is length 5, the two vectors of length 5, you look at, hey, first coordinate, are they similar? And second coordinate, are they similar, and so on. Okay. So one Hamming distance is just saying that cat vector and dog vector, if you remember, there's going to be one location where cat will be 1, and it will be, and for dog vector, that location will be 0. And for the other side, it will be exactly the opposite. So if you think of the
that's a reference to the one-hot encoding. Right?
Yeah, one-hot encoded vector representations. Yes. So those two are one Hamming distance apart. Actually, maybe two Hamming distance apart. So because the two locations are different. Sorry. Yeah. I mean, one or two, but they're basically different but constant. And all words. So any pair of words in the one-hot representation have the same distance between them. If you think of Euclidean distance, even forget about our Hamming distance. Think of Euclidean distance between the one-hot encoded representations. Everybody has the same distance, which is square root 2. Right. So they're all equidistant. So they are not different from each other in one-hot encoded representation. But the outputs, we want similar probability vectors because they have similar nearby words. So that's why word vectors will have that information. Yeah, Hamming distance is a distance measure typically for non-numeric, like strings, for example, like DNA sequence. If you have a DNA sequence of length 10, another DNA sequence of length 10, number of places where it's different is the distance measure here. Distance is defined to be equal to, hey, look at the two strings, look at coordinate wise they're equal or not. Number of times they're not equal is the count, is the distance.
So in that imaginary space, whatever it may be, we are calculating the Euclidean distance because the outputs are either 0 or 1.
Yes. But Hamming distance is a concept in itself, right? So if you have a space of strings like DNS strings, you can talk about number of locations that are different to be a distance metric among the on this space of strings. Okay? So it's more relevant for like strings and stuff. It's not very doesn't make sense for numerical things. Yeah, so actually that's pretty much of word to vec. Some couple of details. One is that each of the weight matrix, if you think of 10,000 as the number of vocabulary, and it's not 10,000, okay, number of English words is actually much more than 10,000. So it depends on how you count things. Okay, so the moment you add like pairs of words to be also valid words in some sense, then you are like really exploding the number of how much your vocabulary size is. So if you think of our example, already it's like, let's say 300 is a number of neurons in the hidden layer, then 300 times 10,000, right? So which is about 3 million parameters in each of the matrix. There's a input to hidden and hidden to output, so two matrices. I'm kind of ignoring biases, by the way, so but you can add biases, no issues. Okay. But about 3 million parameters on each side. So it's already 6 million numbers just for a really stock illustration here. So you can imagine if you're trying to deal with the English language, the number of numbers you need to have in the matrices, right? So that's a lot of, so you need a lot of data to train, even though such a simple network, because the problem is you want a representation for each word. And so you need to have those many parameters. And so people have figured out some tricks, again, similar to the tricks that we saw, batch normalization or dropout and so on. These are tricks specific to word2vec. One is, these are types of processing ideas that you would also get. Okay, any typical data scientist or business analyst, for example, if you want to train, there may be too many pairs with the first word being the, and then the next word being, whatever the word that's in the sentence. And so what you can do is kind of try to not use too many of such pairs. Okay, so for example, you can kind of shrink your data by saying, hey, I don't want to use the pair d comma something else. Let's say I want to use them only with the frequency which d appears. If d as the word is appearing too many times, maybe I want to use that pair a little bit lesser. These are just pre-processing. This is just a pre-processing trick. You can also make common phrases as single words. For example, if phrases have themselves some meaning, if you split it out, then there's going to be a problem. Okay, so like pairs of words or triplets of words, you can just make them words themselves. And also there's an interesting trick called negative sampling, which you'll see in recommendation systems as well, which is that if you think of input to output, even for this small network, given single input, you are getting 10,000 scores in our illustration, and then you are actually 10,000 scores are being produced. But if you focus on one score, that one score is going to influence, if you think of cross entropy loss, right? So let's say there's a right word, and the right word's probability for the right word is some number, and so you take the negative log of that, negative log of that probability. So you have the loss value for that example. Now, if you do a backward pass, it's going to touch a lot of numbers. Okay, so it's going to touch a lot of numbers. So instead of so what do you mean will touch a lot of numbers? Remember our number of parameters in for example, the word side is 6 million. Sorry, 3 million. Right? 3 million parameters from going from 10,000 to 300, and there's another 300 to 10,000. So the 3 million plus 3 million number of parameters. So negative sampling is the idea that, hey, you don't have to, when you're thinking of a forward pass for a pair of words, you don't have to think of the output space to be the full 10,000. You can think of the output space to be like the true word and then some other 100 other words. Okay, so every time you're doing a forward pass, you're thinking of a network where you're kind of ignoring all the other words. Okay, so that kind of at least makes the output side much smaller, like let's say 100 words or something, 100 outputs. But every time you want to include the word that is part of your training, and then you have a smaller smaller number of numbers to update. Okay? So that's the idea. So otherwise you'll have to update a lot of other numbers. Is the idea clear or it's not? Okay, let me actually spend one more second here. So basically, if you think of this, right? So let's say the right word, let's say for ants, the right word is car, okay, for simplicity. Negative sampling is just saying that in the regular situation, if you remember e to the power, so this is the probability, right? So this is the probability for that coordinate. If you remember, this x is a score, right? E to the power x, remember, if once you have a score vector, 10,000 score vector, 10,000 dimensional score vector, you're going to produce this e to the power scores and then divide by, which is a softmax operation. So if you imagine, this is so in the denominator, there's e to the power scores of all the 9,999 other scores as well. Okay. But if you remember, all these other scores are produced by many of the other rows. So in each backprop for a pair of example, all the parameters are getting touched. Okay. So it's because the denominator has 10,000 terms. Okay, so all I'm saying is negative sampling just kind of shrinks the number of scores and therefore the number of rows of the, let's say, the output matrix that are being touched. Okay, so it's an interesting idea to kind of reduce the complexity of backprop. Yeah, only update the weights of neurons corresponding to the to a few non-nearby words. So you have a nearby word, let's say some target word, and some other random 10, 20 words is the only ones that you focus when you're trying doing the backprop. Okay, so that's what's happening here. Yeah, and so here is some example words, and so these are just chosen so that to show that they don't just have single words, they actually have all these types of phrases as well. So you can see DC portable starters. It's not really a single word. It's like three separate words, but they have been merged into a single word. Okay, so therefore the vocabulary size actually for Word2Vec is actually huge. Okay, it's not exactly, it doesn't correspond to the English dictionary. Much bigger than that. And actually, you can. There are many software packages which kind of give you this pre-trained word embedding. So GenSim is one of them, but there are others. Okay, so from GenSim, for example, we downloaded this 300-dimensional Google. I mean, I don't show the download link, but it tells you how to download it. Okay, on the package documentation site. So you can see, for example, you get the model, which is a Word2Vec model, and then you say, hey, what is the most similar words to good? Good has its own representation, 300-dimensional representation. This function is just saying, hey, what are the nearest neighbors to the word, the vector corresponding to good? Okay, and you can see the words are great, and there's also an antonym here: bad, terrific, decent, nice, excellent. So you can get a sense of whether they're well embedded or not. Okay. Yeah, so I guess one small comment about the second version, skipgram. Okay, so I didn't mention what skipgram means. Skipgram is exactly this. So yeah, so gram is just a I guess from historical reasons, n-gram, 1 gram. We have used these phrases before. Okay. So n-gram, for example, the 5-word sequence that we were picking up in the previous illustration, that's a 5 gram. Okay, it's just called a 5 gram. So skip gram just means we are trying to, given an input word, we're just trying to kind of predict one of the grams. Okay, so we're just like nearby grams. So nearby word, and that's why it's called skip gram. Okay, and so that's on the right side. Okay, so it's given a word, trying to predict the nearby word, nearby left word, nearby 2 words to the left, and word to the right, and 2 words to the right. Okay, that's what is going on essentially. Okay, so the left kind of figure should tell you, hey, given each word, I want to predict the 2 to the left, to the right. Basically, that's the diagram here. The continuous bag of words representation is the opposite, where given basically a file length sequence, you are looking at 2 to the left and 2 to the right to predict what was in the center. Okay, so it's very similar to the illustration. Illustration was saying valid or not. Here we're actually trying to predict the missing word. Okay, so that's the CBOW version. Again, this is the same, like it's exactly looks like opposite of the skipgram version. In fact, that's why there's 2 prediction tasks are very similar. Okay, so given single word, predict the 4 words. Given the 4 words, predict the single word. Essentially, that's what it's pointing down to. Okay. Any questions about this? Yeah.
The Word2Vec model.
Yeah.
Has been trained on entire English language.
Yeah, specific, this Google News data set. It's not like this is a specific corpus. So the way you train is you kind of are limited by the corpus that you have, like Wikipedia corpus or Google News dataset corpus. There are many such corpora. You can, like for example, I think Common Crawl gives you a crawl of the internet itself, right? So there are different corpora from which you can train. So Google News dataset they had, and they had the and so they created those words. Remember, like these types of words that you see in the previous slide. And once they created this, they did the embeddings for these. Yeah.
It is very likely that whatever words that we give to the embedding, so we give to the model, it must have been seen by the model previously by training.
Yeah, the word itself should be seen in some context. Yeah.
What will happen in the case the model hasn't seen the word?
It's a completely new word. It will not have its representation, right? So it's like saying in a dictionary, I don't have keys. If it's a new key, then you'll say no, it's not found, right? Yeah. I mean, the most simplest setting is that. I mean, yeah, I mean, there could be other fixes, but they need some extra metadata. So given just this dictionary of keys and values, I don't see how you can get for a completely new word that's what is not there in the corpus at all, and for which you would need an embedding. Yeah, but that's a good question. So if you already had word embeddings and you have a new word and some new sentences related to the word, how would you get this embeddings? Like this incremental question is interesting, and that could be a project by itself. I mean, it's not that it's solved. Okay, it is solved, but it's an interesting problem to try out.
Is there any reason why Google chose the news data set? Because the word representation that we get would be akin to how news is written.
Yes.
And that doesn't necessarily encompass how we talk, for example.
Oh, talking is even harder, right? So generally you go to books data sets. I mean, corpus, which is like Project Gutenberg or something like that. That's the type of data set people used to use. This was actually a big delta from before, in the sense that they were at least willing to go beyond textbook corpus. And the moment you get to how we speak or how we interact on social media, that language is also very, very different from what you see in books or on news articles. At least these are a little bit formal. Yeah, there's difference. I mean, they just picked it for the scale. I think the ideas were there before this prediction, using prediction approaches to get embedding. It's just at the scale at which they did it and were able to kind of disseminate trained embeddings. That was the big thing. Yeah.
I didn't really understand whether we are setting like a preference for the word to the left and the word to the right, or they have the exact same value.
Oh, they
on the first method we covered.
Yeah. So if you think of this, right? So if I give an example, so let's focus on one example, right? So there's from some 5 words. The third word is the input, and what the word to vec skipgram model is trying to say, hey, given the third word, try to predict the second word, try to predict the first word, try to predict the fourth word, try to predict the fifth word. And all these are equally weighted examples. So there are basically 4. I think we showed in the quick, in that sentence, we showed like 4 training pairs being created. Those are these 4 training pairs. Here it's all overlapped into a single one, saying, hey, one word is trying to predict 4 words at the same time. That's not the case. As you saw in the network, that we will have 4 examples, and each word should predict. So the third word should first predict the second word. In the second example, this word should predict this one word to the left, and so on. So, but they're all equally weighted examples. Yeah.
Regarding the stemming of the words, we saw that this handles stemming at some extent. That word.
You don't have to pre-process. I mean, because the words which are almost in the similar, like maybe an extra, like a plural or ing, or the usual types of suffixes that you can get, they appear in similar contexts, so you don't have to deal with them. But you can, nothing hurts you from doing stemming or lemmatization if you want.
Okay.
Yeah. Okay. But that's typically people don't train again, because as you saw here, at this scale they have trained it and they did a lot of engineering tricks, and that's what you'll find. I briefly mentioned a couple of tricks here, but it's not easy to train it because of the scale. It just takes too long. Even the network is simple, but so if you want to do it yourself on a very specific domain, then you can certainly do stemming and extra pre-processing you want to do, and then get these types of embeddings. Yeah. Okay, so there's some links to the implementations actually. Maybe it's a little bit, check whether this exact link works. So TensorFlow, which is I guess by Google, they have an implementation. But other people have also implemented the same ideas. Okay, it's the same idea. Replicate the paper, replicate the way it's built. So in general NLP, we're gonna get back to NLP in the next lecture, but I wanted to briefly mention some popular packages here. Next lecture's NLP will be mostly about transformer architecture. So it's really something that was developed in the past 4 years. Okay, some specific new neural network architecture. So each lecture we've been kind of looking at new neural network architectures. Okay. So last lecture was about this word embedding business. This lecture will be about RNNs. Next lecture will be about something called transformers. And if you remember, first lecture was about feed-forward network. Second lecture was about convolutional neural networks. So we kind of are trying to cover one popular network each session. Just like wanted to kind of find out that there are some very popular packages you should try out, which have, for example, if you want to do lemmatization or stemming and some of these words here. Some of you who have done NLP or text analytics, you may recognize this. If not, don't worry about it. Some of them are pre-processing steps. Some of them are just definitions of tasks. Like, so NLP is not just about predicting the next word, like a language model, like what we do in language model. For example, there are tasks like named entity recognition, part of speech tagging. These are all typical types of tasks that you do in NLP. Okay. There are many other problems actually. If you recall at the beginning of the slide deck, there's question answering and things like that, right? So these are some example packages like GenSim, NLTK, Stacy, TextBlob, Python, and there are actually many more. Okay. So here's very short list. Okay, so with that, let's actually switch gears and talk about RNNs. Okay, so again, to recap, the objective is understand what is sequential, what are some example sequential problems or use cases, understand what is RNN bringing to the table, this new architecture, kind of go into the details of a specific variant of that RNN architecture, which is called LSTM, and if possible, like link it to existing temporal or time series type of models that you might have seen before. If you have not seen it, don't worry, it's not needed. But if you know some time series ideas, then we'll try to kind of say when this how much there's an overlap. Like he mentioned that you can use LSTMs for stock price prediction, right? You can also use regular time series models. You can actually just use any regular machine learning method, like even a gradient boosted decision tree or an SVM, to also make time series predictions. Okay, so let's make those connections when during the discussion. So the outline, we'll start with the architecture definition. It's very similar to how we introduced feed-forward network and then a convolutional layer. Okay, so just like feed-forward network is going from some input tensor to some output tensor, but there was not much crazy thing going on. But the moment you had a con layer, there's some notion of filters and things like that. So very similarly, the original RNN architecture is a base template with the simplest stuff first. And then LSTM is a popular variant, okay, some variation of the original architecture where there's some extra stuff going on, but achieves the same purpose, okay, which is sequence to sequence modeling. So given a sequence or a kind of a time series as an input, you can produce a prediction, which could be a single item or a sequence of items. Okay, so that's why. So that's the second thing, and then if there's time, we'll talk about other RNN applications, and also, we will kind of look at sequence learning in general, like in general, what types of sequence problems there are, and I think we'll look at a couple of applications, okay, mostly translation and things like that. So we may not be able to. So if we have time, which I'm not sure of, but if we have time, we'll talk about something called attention mechanism. Okay, so next lecture will be the interesting one where we'll talk about transformers and also something called attention. So attention is a word that is very general, like attention means something else, but in the parlance of, or in the context of deep learning, it means a couple of things. So we'll look at them. So let's start with RNN. So yeah. See, I could probably full screen it. Okay, there was a chat. Actually, let me check what the comment was. I don't know the comment. So Okay, let's actually move forward. Okay, so now we are stepping back and trying to go from applications, model, and again applications. Okay, so what are the applications? What types of applications do you want to see now, which we have not covered with CNNs and word-to-vec and all the previous things that we've seen, feed-forward networks. So the application is we want to move away from the leftmost side. The leftmost side is where there's some input vector, image, something like that, and then we want to produce one output. Okay, that could be a class or a numeric score or whatever it is. So it's basically fixed input and fixed output. So it's like a multi-class classification problem, for example, fits into this leftmost situation. Red boxes are inputs, blue boxes are outputs, and here I say RNN state because the center ones may involve RNNs, but in general, like input output, and think of the center one to be some function mapping from input output. So far we've seen input output relations where it's a fixed input, fixed in the sense that fixed size. Okay, either the vector length is 10, it's going to be 10 for when you train, when you test, everything, it's always going to be 10. And same thing with the output. So when you're training at an output class, number of classes 10, it's going to be the same every time. Now there could be some other types of problems, which is literally the next 4 blocks, where either on either side there could be there's no fixed size input. Okay, for example, the next one is saying image captioning. Image captioning is the problem where input is an image, like the usual CIFAR 10 image or something like that, and then output is actually a caption in text. Okay, so what is happening in the image typically? A caption should capture something about the image, so that could be 3 words or that could be 10 words. Okay, so the output size is not fixed. Okay. Similarly, sentiment analysis is something that we've seen before. Sentence classification, where the input was actually not fixed, right? So a sentence could have 10 words, or a sentence could have 30 words, but at the end of the day, you want to make one prediction, which is some class of the sentence, right? Similarly, you can combine these two, one to many and many to one, to say many to many. And this is where, for example, think of language translation. You have a sentence in English, it could be 7 words. You have a sentence in, let's say, French, it could be 3 words. Okay, so and the 7 and 3 could change depending on the sentence pair. Right? And the many to many themselves could be slightly different in the situation where in this one you're actually, so language translation is also called machine translation, by the way. So where you're waiting till the last input to produce the first output. So you can see that first input, second input, third input. Once the third input is passed, think of left to right as some sort of time step or some linear ordering, where only when the last input is passed, you're producing the first output. Okay. Whereas in the rightmost one, the moment first input is passed, you're producing the first output, and when the second input is passed, you're producing the second output. So a slight difference between them, but both are many to many examples. Okay. So second one is where for every input you may have to make classification. It's just that you need to remember what also probably you did before. Okay. Okay, so what is the extreme starting point is the idea of persistence. Like you need to remember, so you need context to make the current prediction. Okay, so feed-forward neural networks and CNNs, at least inherently, if you use them in the straightforward manner, the way we have defined it in the previous lectures, they don't model persistence because they have an input, let's say an image, and they make they predict the class based on that. It's not that you have explicitly passed the previous image or the previous 3 images or anything like that. You're not, right? So in that sense, there's no persistence. It's like a forgetful situation where you send an image, maybe it's an image of a dog, it misclassifies it as a cat, let's say. The next image you send is also, let's say, is a dog, because it misclassified, and it has nothing to do with the next time it's gonna misclassify or not. So it's like independent situations, right? IID type of situation. But whereas maybe you need that persistence. Okay, for example, if you're doing a video processing, then you can classify like scenes in a movie as being scene 1 versus scene 2 versus scene 3. Maybe it's unclear, at least in the naive way, how to pass that information to a CNN. You can actually, it's not complicated, but at least the version that we've seen in previous lectures, there's no persistence. Okay, and that's what we want to capture. So to capture that, it's a very straightforward idea here. to capture persistence, which is via this idea of recurrent neural networks. Recurrent just means, I guess, is the word being used to say, hey, we want to capture persistence. It's as follows, which is you start with some function, okay, some function. So if you ignore the this looping type of arrow, which is this, by the way, left hand side is called a rolled diagram. So ignore the arrow for a second. So you can imagine, hey, given input, produce an output. Okay, so given blue input, produce a red output. Okay, so that's clear, right? That's a usual situation. So given some input, produce an output. So think of this block A to be some function. Okay, some function. So Python function, def some function, takes some input, produces some output. Now, to capture persistence, the RNN idea is to call that function again and again and again, but just pass the next input, the next input, the next input, and so on. Okay, so now, and of course, there has to be some notion of persistence. So this function is not just a single input, single output situation, single input, single output function, but it's a 2 input, 2 output function. Okay, so now you have, so why 2 input, 2 output from single input, single output is only because you want to say, hey, take the current input, but also get some information from the previous thing that you did. Okay, so it's just a notion of persistence being captured here, where when I'm trying to, let's say, process my current input, let's say the third word of the sentence, I take into account whatever is produced by the previous time this function was called. And that function itself is also trying to take into account what previous time another function was called. The same function was called with some previous inputs. So, okay, so that's how you're trying to remember. So my current prediction, let's say whatever prediction I'm making, h or some class, depends on the previous outputs as well. So think of x0, x1, x2, all of them together are influencing h2. So if you just think of the like computational graph view, all we're saying is, hey, there's an arrow from here all the way to h2. There's an arrow from here all the way to h2. There's an arrow from here to h2. So h2 is influenced by some computation that's happening from all these three. Whereas h1 is being influenced by computation happening from x0 and x1. Okay, so and so on. So this right hand side is a diagram which is actually the typical computational graph. The short form for that, instead of, that we're going to use the same function again and again. Okay, so we just kind of put a self loop there. Okay, now you can imagine if my input was only length 3, then this unrolled diagram will only have 3 such blocks, green blocks. If my input was length 10, then I have 10 times those green blocks, because I'll call the same function 10 times. Okay, now the function is just 2 input, 2 output, and much of the effort in the rest of the class is just saying, hey, what is inside that green box? Okay, that's all. So this is essentially a recurrent neural network architecture. In fact, yeah. So for example, the sequence of inputs, this blue things x0, x1, x2, x3, could be images, words, or just numbers. Okay, time series numbers, for example. So if you want to make stock price prediction or something, so x0, x1, x2, x3 would be just the stock prices of the previous days or returns for the previous days. Okay. Now, what is h naughts? I'm using h naught only because I want to call them hidden vectors at some point. But you can also think of output layer to be almost hidden vector as well, in the sense that you're just labeling them as hidden vectors or output. So that's why we're calling it h naught, h1, and so on. So let's actually so this function a here, or this block of computation a, they accept an input, they give out an output. They also accept an output from the previous time a was used, and they send an output to the next time a will be called, if it is called. Okay. So these inputs and outputs are parts of sequences, right? There's an ordering. Okay. Typically, you would think of time ordering, but doesn't have a time, but some ordering. Okay. But typically, we'll think of them as time. So what remains to be, so if you don't care about the previous couple of slides, all you need to think of as a recurrent architecture is just this. Okay, it's just the architecture length just depends on what is your current input length. Okay, so if your input length is 3 words, then the architecture diagram that you would represent for that forward pass will just have 3 such green blocks. If you input at that point of time had 5 inputs, then you just your diagram for the architecture for that pass would have just five green blocks. Okay. So now, and explicitly, I've also mentioned that these green blocks are all the same blocks, the same functions, so they have the same parameters. Okay, it's not like layers with different parameters. So don't think of these as if you kind of analogy with linear whatever free-form neural networks, it's not that this is a layer, this is a different layer, this is a different layer. If this is a layer, then it's the same layer, it's the same layer, it's the same layer. Okay.
So this XT will represent number of features in one row of the input data.
Yeah, you can think of XT as a vector. Yeah, it's a feature vector.
So the T represents the number of columns that one row of the input would have.
Oh, you're trying to equate it to data matrix where T would be the T throw or something. No, actually here, so I think the best analogy is with respect to sentences, because I don't want to map it to tabular data because there's confusion of indexing. Just think of X0 to XT as like the T words of one sentence. Okay. Yeah. We'll talk about tabular data later, if it makes sense, because I don't want to confuse with indexing at the moment.
But this is still one input with those
One
number of words being fed at a given number.
Yeah, so if the sentence has a little t number of words, then word representation for the first word, word representation the second word, word representation the third word, and so on. And you want to kind of make so think of trying to say sentence classification, right? So first word, second word, third word, fourth word. Maybe it's producing all these outputs, but we don't care about all the other outputs. We only want to care about, let's say, the last output being the true class or not. Like let's say positive sentiment versus negative sentiment or something like that.
So at every iteration, is it learning or?
No, we are only focusing on forward pass. As I said, like first we want to understand the forward pass. The learning part would be, hey, there's something to be learned, which is this parameters theta. How we learn, as I said, at the end of the day, it's just going to be, if you can define this as a PyTorch model, it's just going to be lost or backward at the end of the day. But what you want to learn, and we'll talk about like how exactly the capturing persistence, right? So it's capturing persistence via this parameters theta. And at training time, we are actually learning theta such that, while trying to produce, let's say the last output HT, let's say positive and negative sentiment, it is getting influenced by all these previous ones, right? So this is the computational graph while making the last prediction. It has a connection, right? So X0 is going through a lot of transformations to say what, have some say in what the class level could be. Whereas XT is, is not going through a lot of things. It's only going through one green block to say what could, could it to influence what label could be. Okay. So let's actually see maybe some more diagrams to get a feel for what's going. Yeah. Oh, this H0. Yeah, good point. Good point. So we will look at what this H0 is and what's the difference between, so if it's the same or not. Typically, in the two architectures we will see today. So just to give a teaser, we'll look at two RNN, two openings of this green box. Okay, in both of them, actually, this H0 and this forward arrow will be the same. Okay, so you can actually think of them as the same for now. Yeah, in LSTM there's a little bit more complication, but yeah, at the end, it just happens that these two are the same. Okay, think of function return a comma a in a list where a is something that it has to return. Instead of returning only once, it's just making a list and returning twice. Okay. Okay, so some diagram before we open that green box A to kind of understand how is it related to neural network. So far we have not introduced neural network at all. Just think of that function as A, and we said this is how it would deal with variable length inputs and variable length inputs outputs. So let's think. So this is just a legend here. So neural network layer is going to be a green box, and all the arrows that you see are generally vectors. Okay, so some vector being passed on to another location. So generally, if there's an arrow from a box to a box, it's going to be a vector being output from one box and input to another box. Okay, and like this type of an arrow with two tails, this is concatenation, and again two arrowheads, this is a copy. Okay, so here's a opening. It's actually a very simple idea. The vanilla RNN is simpler than, it's like very similar to your one hidden layer neural network level. Okay, so here is the opening for the box A. Okay, so as I said, A is being called multiple times, so we can only focus. It's okay if we focus only on one of these boxes because it's all the same. So the box is as follows, right? XT is being concatenated with some previous input. So if there's a previous input, get it, right? That's the input. Two argument inputs, right? So previous A is processing whatever it produced. Let's call it. In fact, you can see it. The HT itself is like being copied. So HT -1 is input, and xt is input. So those two are concatenated into a longer vector, and then being passed through a neural network layer. Okay, this yellow box here, neural network layer. And then in this neural network layer is just, when I say layer, it's just a feedforward neural network layer. And so there's a weight times input plus bias. Okay, and then there's a tanh nonlinearity applied. Okay, why tanh, why not ReLU, why not something else? So tanh is the canonical thing that's typically used in these networks. So tanh is used, and then whatever is the output vector, that's just whatever was produced here with activation vector is either written as a HT at this point, and also passed forward if it is needed for the next computation. So that's it. That's the RNN piece. Okay, so you can define this using nn.module or by extending the class easily in PyTorch, for example. Okay, so this is the vanilla RNN, and so it basically has a single hidden layer with a tarnished nonlinearity. And here is the code, right? So here I'm not even looking at PyTorch. Let's say if you just have if you want to kind of write it down in NumPy, here's how code looks like. You have an RNN class, and for simplicity, I just made it to have a local. So generally, the A box should have just the parameters. The parameters of this green box are just the weights of this neural network layer, which is just the weight and bias. Only two things. For simplicity, I just added one more, which is the which is not really parameter, it's just a state. Okay, either I mean, either you can keep the h, whenever it produces a h, you can either keep it outside and keep track of it to pass it to the next time it's called, or you can keep it inside. So w and b is clear, right? Those are two parameters. H is initially 0, so h is like current. What did I produce? Now, if you think of a step in RNN, a step or stage or one computation of A, it takes xt as an input. Okay, ideally you should take h from before, but since I'm anyway remembering it, so let's call it, that's present already. So xt and h are concatenated. You can see that self.h comma xt is concatenated using a np.h stack operation. And then I'm doing an np.dot with my current w and adding the bias. So it's basically wx plus b, where instead of x itself, I'm concatenating with ht and then multiplying with the linear transformation. Then I'm just calling tan h on it, and that's h, and so that's overriding the previous h value here. I mean, I can track this h stuff outside, but you can track it inside as well. So if you think of RNN 3, 4, so length of the hidden vector is 3 and length of the inputs are 4. So I'm always passing 4-dimensional inputs, and inside the h, the tarnished layer is always producing a 3-dimensional output, which is three neurons. Then let's say I have 5 words or 5 such vectors. Then here I'm just creating some random vectors, but basically dot step will produce ht, and you can do it 5 times. Okay, so that's pretty much it. Like you're getting here I'm just arbitrarily creating an xt, but you can imagine how to do it, right? If you have a 5-dimensional 5, so you have 5 vectors, because maybe you have a 5-length sentence, for example. So 5-length sentence, 5 words. Look at their word vector representations. There will be 5 such vectors, and so you'll just pass them one after the other. Okay, so the reason why I use that 3 and 4 is because there's an illustration in the next slide, kind of further delving into some delving into the RNN operation in RNN operation, and we'll use this example, the language model example. So very similar to last lecture, we talked about some very, as basically a warm up. We looked at some models, right? We looked at Naive, we looked at Markov model, we looked at sentence classification using CNN. We looked at something called something related to topic modeling or unsupervised learning called latent digital allocation, LDA, right? We looked at a few warm-up models last time. I just call it warm-up because it's not really about deep learning, but they were other models basically. So here, and so when we're talking about Markov model, there we mentioned language model. Okay, so we mentioned language modeling. What is language modeling? Language modeling is just saying, hey, think of English language. Language models, what they do is, given any previous context or previous words, try to predict the next word that should come. Okay, that's all. So language models are models which are just predictive models, which given previous 3 words, try to predict the next word. Given previous 4 words, try to predict the next words. Okay. Even if you can do that, then you can imagine you can start with some couple of words, and the model can keep predicting what the next word could be, and it'll generate a sentence, for example. Okay. So that's what a language model is. So for simplicity, let's think of a character level language model, so that it's easy to kind of illustrate the points. So character level is just at the level of not word, but at the level of a single character in the English alphabet. Okay. So what do you do with how do you build such a language model? So we're talking about an application here, okay, just to kind of better sense of the RNN model. So what do? You have a large text database, a data set, okay, and then what you want to do, predict the probability of the next character given the sequence of previous characters. Let's say you pick let's say you fix the if you fix the previous characters, then it's not really, you can probably get away with not using RNN. But if you want to use sequence of previous characters, the number of previous characters can change, right? So for example, and we'll see in the next slide, the number of previous characters can be 1 or 2 or 3 or 4 depending on where you are in the word, right? So basically, applications of in general language models is that they let you generate new text. So I don't know if any of you played around with GPT-3 or any of these web-based demos where people show, hey, write something and it will auto-generate some text. So that's an application of language modeling. Okay. So but character language model that we are talking about is just for illustration's sake here. So here's an example, right? So let's say our English vocabulary has only 4 letters. Okay, that's not the case, but let's say only 4 letters: H, E, L, and O. Okay, so 4 letters, and we have one particular we have one training data point, which is, let's say the word is H, E, L, L, O. Okay, so which means that for us, it's like this is the training sequence, H, E, L, L, O. I want to produce next characters given previous characters. Okay, so from this training sequence, from, for example, one sentence of training sequence, I can produce 10. These are the training examples I can produce. Given H, I can produce E. I can try to produce E. Given HE, I can produce L. Given HEL, I produce L, and so on. So in training, what I want is, given H, the probability of E, it's like a multi-class classification. So our output space is going to be 4 scores, okay, 4 scores, and we want to produce a score for E to be high when this example is passed. When this example is passed, I want the probability for L coordinate to be high, and so on. Okay. So let's say we, for simplicity, we also have an embedding for these characters. Maybe like word to vec, we already had done some embedding computation, and so each character has a 4-dimensional vector. Okay. So if not embedding, let's say it's simple one-hot encoding actually for simplicity, which means that H will have 1 0 0 0, E will have 0 1 0 0, and so on. Okay. So here's an example of this HELLO being trained. Okay. So HELLO, because it has 5, because it has 5 words here, so 5 letters here. There are 4, I guess, A blocks. Okay, this green block still corresponds to those RNN steps. Okay, instead of HELLO, there was maybe a 10-letter word. Okay, with still those 4 characters. Then this green boxes would be like 9 in number or 10 in number, whatever it is. Okay. So let's actually focus on what's going on, right? So when you pass H, okay, let's say the encoding of this character is one-hot encoding for simplicity. So you're passing H, which is 1 0 0 0. Okay. Now that green box is taking this as input. Initially, there's no other, there's no previous green box's output to take care of. So it's producing some 3 numbers, hidden vector 3 numbers. Okay. And those 3 numbers, and we didn't see it earlier, those hidden 3 numbers, because we want a 4-dimensional output, like 4 scores, those 3 numbers are further transformed using an output layer. We're not seeing that layer in the RNN definition earlier. Okay, but we need to map that hidden vector again to some, like if you have 2 classes, then you need to map it to 2 numbers. If you have 10 classes, you need to map it to 10 numbers. So there has to be again a linear transformation. Okay, so that's what's going on. So from green numbers, which are hidden outputs, to a 4 numbers that's being produced. Okay, and then at this point of time itself, you have 4 numbers. These are scores. You want the score for the true class, which is E, to be highest among all the 4 numbers that you produce. Okay, so that's basically captured using cross entropy loss. So do a softmax operation, do a cross entropy computation. That'll ensure that if your score for E is not high, then your loss is high. Okay, And what are you trying to train? The parameters of the green boxes. Okay. So now next step, E is passed in. You're getting also these three numbers from before. So these three numbers and this E vector are concatenated. Okay. And then pass through that tanh, for example, that RNN box, and you're producing again three numbers. And again, those three numbers are used to make a current prediction, which is hopefully L coordinate corresponding to L is the highest. It's not the case here, but if you're going to focus on that. And then you produce, and then you pass these three numbers to the next step and so on. So this really opening up how the RNN operation is going on. So any questions about this? Yeah.
What if we have a word that we have not trained on and we're trying to predict the next letter?
Yeah.
And let's say something like this happens when there are two L's.
Yeah.
So isn't there a probability that we start going into a loop?
Yes. Yes. So these. So how do you so at training time there is no confusion of loop. At training time we know exactly what the reference, what the true label should be, and we do cross entropy loss and we learn parameters. Once the model is trained, there is a possibility that you may go into loop that you're talking about. There are ways to fix it. We'll address it at the end. Okay, so because it is an important concern that. But what saves us is the fact that we are going to produce a distribution of our next words or next characters, and so you can sample from it. And so if you sample from it, then there's less chance that you will come back to L again and again and again and again, because there's so many words in the dictionary that. So there are some ways to fix it. Let's come back to that later.
So we have only one set of parameters for each green block.
I mean, although there are 4 green blocks here, we only have one set of parameters. Yes, it's not like there's no other parameters. The only parameters are just this W and bias. So although the green block is called like 4 times or 5 times here, right, in this example here, but the green block will have just the W and bias, W and B. It's the same W and B, so it's only instantiated once.
What kind of concatenation is happening between the?
It's just a usual vector concatenation. It's just one below the other. Yeah. So you can just see this type NP H stack or V stack, whatever you want to call it, but basically just 2 vectors being one below the other. Yeah. Okay, so just to complete the picture, some more extra points is that cross entropy loss. Okay, and that's clear here. You want to say E, and you got a distribution of scores. I mean, collection of scores. You transform them by softmax and just do cross entropy at each of the next letter. Okay, so if you have 10 letters in the word, then there'll be 10 cross entropy terms. If you have 3, like in this case, you have 4 next letters to talk about, then you'll only have 4 terms in the cross entropy. So it's not fixed size. Okay, so that's one important part with RNN models. Yeah, and so you need a persistence because of this example here. When the first time L is produced, L is input, the next character should be L, but the second time L is input, your next character should be O. And how do you know that? Because you kind of have that information from the previous time A was executed. Okay, that green cell was executed. Okay, so let's take a break now. Yeah, and resume at 5:25. And if you have questions, you can ask me in between.
Professor, we're not able to hear you.
Sorry, didn't realize that. Can you hear me now?
Yeah, yes, we can.
Okay, so let me take 30 seconds to just repeat what I said. I can't. Does not go up and down now. Yeah, so we just started talking about, and we're trying to motivate towards a different architecture for the RNN cell, which is the green cell. And just to recap, we were trying to use RNNs because we want to capture information. But the question is, does it capture information enough, or is there a better design, a better variant which can capture information better? Okay. Turns out if the information is recent enough, then RNNs are able to do fine. But information is not recent enough, which is this second example where the information like UIC appears long before you need it to make the next word prediction. For example, maybe I went to UIC and you say a couple of other sentences, and then you say I lived in dash. The dash has to be Chicago. If we know there's a place, but we don't know exactly what could be the place because it has to rely on information that was long time ago, and that's being shown. Oh, what's going on? Yeah, that's being shown in this slide where sometimes information is recent enough, like this H3 is being influenced enough by X1 and X0 to make the right prediction. That's in language modeling. But this T+1 may not be influenced by X0 and X1 because of this long chain. And so how do you kind of fix this? And there's no kind of in theory answer how to fix this long range information. I mean, there are a couple of fixes, but LSTMs are one empirically validated solution to kind of rewire the green box, the RNN cell or the RNN function in such a way that it turns out empirically that it is able to retain information slightly better, in fact sometimes much better than the vanilla RNN architecture. Okay, so and LSTM just stands for long short-term memory. It's just a name given to it, and it's just a regular function. Okay, it doesn't have extra storage or some local memory as such. Okay, it's just a function. So let's look at what the details of this function are. It's basically designed to avoid this long-range issue that we saw in which you may see in the vanilla RNN architecture if you use it. Okay, and so for that, as I said, it's basically empirically driven. There is interpretation, and we're going to go through the interpretation of how it maintains long-range information. But strength is actually really empirical performance. Okay, so it performs really well, and so kind of is one of the popular, I guess, starting points for these types of sequential modeling problems that you may have. Okay, so the structure is very similar. It's just that the block inside the green box has a lot more things going on than the simple tanh layer that was there before. Okay, so if you look at this A box, and by the way, it's just the same A box, now has more parameters, right? So if you remember, this yellow things were neural network layers, so they'll have parameters. Okay, so nothing else is parameters. So instead of one set of parameters, it looks like now we have four set of parameters. And before we just had this one tanh layer, like the one in the center. It's still the same tanh layer, but now you have these extra bells and whistles basically that try to moderate information such that you kind of capture long-term information. So that's the idea. And so we kind of understand, like, at least interpret it in one way to kind of try to kind of interpret and see why it may capture long-range information. Okay, but this is not the only way. People have experimented many different variations. There's another popular variation called gated recurrent unit, GRU, which is also which is also a replacement for this green box. Okay, and you can vary in many different ways. It's just that some patterns have emerged to be really good. Okay, so let's actually again recap. So yellow means neural network layer, so that's the one with parameters. Now new I guess notation. This pink box circle means a point-wise operation, element-wise operation. Vectors are exactly the same, concatenate and copy. Okay. So now let's really tease apart, and next 10-15 minutes just really understand what's going on inside the A cell. Okay, so now in terms of function signature, something additional has happened, in the sense that previously RNN had 2 inputs, 2 outputs, right? So current input, previous hidden output, and then new hidden output, and maybe output itself. Okay, so in addition to that, those are kind of grayed out here, or basically greened out here. So xt and ht minus 1 and ht and ht, those were same as the vanilla RNN. The one new thing is now in this function, at least in the function is getting an input which is ct minus 1, another thing from the previous execution of the function, and is producing a ct. So it's getting one extra input parameter and output parameter. Basically, if you think of a Python function signature, that's all that's going on. And this has been given, so we're going to interpret it. So we're going to give some names. So it's called a cell state. Okay, and this is, and you can see that, and it's being represented as a vector here. So a vector is input and a vector is being produced in output. The vector is slightly being modified at these 2 locations. Okay, that's what pictorial is going on. So just pointing out inputs and outputs here. So what is the cell state? Okay, so the cell state is the key new, I guess, thing here. The cell state is a vector which hopefully, is run straight down the unrolled network, in the sense that if you think of a really long sentence, there'll be a cell state kind of line in that diagram. And you can see that the number of interactions it's having with the rest of the network is quite small. There's some couple of element-wise operations going on. Okay, some multiplications, you can see. So cross inside means element-wise multiplication of the vector with something else, and addition means some other vector is being added to this vector. Okay, so those are the 2 interactions, and so this, we're kind of saying that this probably is causing information to flow from long time ago. So that's kind of one interpretation, that information can flow along it unchanged if necessary. Okay. And this if necessary is only, so all this is captured by the trained parameters. The trained parameters of the network of the cell, like these 4 networks, are the ones which will ensure that either long information, vector that was generated at the beginning is passed as is, or maybe vector is modified after each call of this green box. Okay. So what's going on? So what are these changes, right? So we'll talk about these changes via the notion of gates. Okay, so gates are just like taps. Okay, so if you you like kitchen tap, right? So this is an example of a gate in the bottom left. So LSTM can add information to the cell state, like it's adding information or whatever, it's changing some information here, information in the sense of vector, by regulating what is called a gate. Okay, so a gate is basically a structure which looks like this. Okay, so basically a gate involves a sigmoid neural network layer, so it needs to have a neural network layer, so yellow box, and a sigma on top of it just means sigmoid layer. So what it's doing, so what is this gate doing, right? So if you think of it functionally, there is some input vector. Gate's operation is to change that input. Okay, how are we going to change it? If the gate control signal is high, let's say high or low. Okay, let's say it's high, then pass the information through, like whatever vector was there, pass it through. If the gate's input control, some vector is like really low, all zeros or something, or maybe negatives, then maybe make the output all zeros. Okay, so that operation mathematically is just this. So V is the input vector is getting element-wise multiplied with some sigmoid of some input. Okay, some input is given U, it's being linearly transformed, and then sigmoid operation is going on. B is being applied to it. Okay, right? So when you apply sigmoid operation, if the transformed version of the U is large, remember sigma is going to be, sigmoid of that is going to be 1, right? So this is the S-type curve. So for U's which are kind of large enough, it's 1. U's which are negative, it's 0. So it's like, so the only thing sigma is producing is some numbers between 0 and 1. Typically, think of that sigma as like a soft version of 0, 1, turning on and turning off. So it's like, so if sigma produces all one vector, it's as if like, hey, V vector unscathed is going out. Okay. If sigma is all zeros, then V vector is completely forgotten. You have zeros now. when sigma is in between 0 and 1, then it's like some smaller strength in each coordinate of the v is being passed, and this is happening at each coordinate. So some coordinates can be passed on as is, some coordinates can also become 0, and some coordinates can have a small multiplier like a amplification factor, okay, on them. So that's a gate, okay, and yeah, I think I explained that. So LSTM actually has 3 gates to control the cell state. Okay, so all the focus is on the cell state because that's the one which is like kind of in the, at least in the picture, it's like kind of not being interacted with much, not too much transformations like the hidden vectors, right? So the first part is forgetting old information. So there's 2 parts actually, 2 big parts, and forgetting old information it involves 1 gate. Okay, so old information just means like CT minus 1. I want to forget some old information, means exactly as a gate like this, and you saw in the figure that there was a gate like this at the top left of the figure. We'll come back to that figure in a couple of slides. So we'll forget old information. Basically, you know, we kind of throw away some information in the cell state, that vector, and how do we forget that information? So we have CT, which is what we want to change. That's like the V in our example. We have a cell state to control it, but what's the input of cell state? Okay, the input of cell state is as simple as just the previous hidden vector and the xt. Okay, so the u in the previous example, generic example, is just going to be ht and xt. Okay, so you take ht and xt, concatenate them together. That's going to be u. Pass it to this gate. The gate is eventually going to control what CT, some coordinates of CT to pass through, some coordinates of CT to set to 0, some coordinates to amplify, de-amplify, whatever it is. Okay, so that's the forgetting all information. That's you know, that's that part. Okay, that's, I guess, is shown here. So you can see that HT and CT concatenated, go through cell, go through the gate, and gate produces some output, and that's going to be element wise multiplied with CT, so that you know, you can so you forget some old information essentially. And there's some explanation here, like maybe there's some gender of the current subject, and you want to forget that gender information if the gender information is actually in one coordinate. It's kind of unlikely, but let's say if there was a gender information in one coordinate, then you want to forget it. Then that's how you modulate it. Okay. Next, let's talk about remembering new information. So remembering new information is a little bit more involved because you need to create first new information and then you can remember it, right? So this involves 2 gates. This involves 1 gate and 1 tarnish layer. So creation of the new information is like using the tarnish layer, just as we saw in the RNN original RNN case, vanilla RNN case. And then how to add it to the cell state. Okay, that's you need a gate to add some information. Okay, so what does that gate do? Instead of like deleting information, it just decides what vector to add to the cell state. Okay, like you can add a cell state. You can add a vector to cell state where each coordinate of the vector could be all zeros, or some coordinates could be positive. So just some additional information to the cell state. Okay. So, and what does tarnish layer do? It creates that new information, like vector that you want to add to the cell state. Okay, so here's the diagram of what's going on. Again, ht minus 1 and xt together produce tarnish, so new information. Yes, tarnish is that new information. After the tarnish is the new information. That's exactly the way as we were doing in vanilla RNN. Okay, but the same ht minus 1 and xt also control a gate. Okay, so the sigma is a gate which, you know, kind of is modulating the new information that you generated. Okay, it's basically saying, hey, you created a new vector. Now I'm going to use the gate to further control whether some coordinates of this new information should be 0 or 1s, or you know, should be left as is, or should be multiplied with zeros, or should they be you know, amplified or something like that. Okay? That's this arrow going on here, and that whatever is the resultant is just being added to the cell state. I think that's grayed out here. We'll kind of come back to this in a second, but that's the addition of new information. Okay. So any questions about this? This is just, we are really going into the details of how this network is laid out. Very similar to how we went to the details of con layers and fully connected layers and so on. Yeah. Okay. So yeah. So the gate operation is very similar. So element-wise amplification, attenuation, whatever, and then add it to the cell state. It's like saying adding the gender of the new subject if you want to the cell state, if this is a new subject that you've encountered in the sentence. And then finally, I mean, so the combined effect of both of them is to forget first and then remember. Okay, so you forget something and then you add something to the cell state. Okay, so that's how you would modify the cell state, and the remaining part is how to create the next HT. Okay, so next HT, and so that is going to be just a the way we're going to create is to make it a transformation of the cell state. Okay, so HT is going to be some kind of modification of the cell state. Okay, so how are we going to do it? We pass the cell state through. Actually, this is not correct. So it's not a tanh layer. It's just a tanh operation. And then we're going to scale it via sigmoid operation. So let me just show you how it looks like. So let's focus on just this part. Okay, just this part, which is, so at this point we've already modulated, as in like we've already done everything that we want to do with the cell state at this point. So cell state started here. We removed something, we added something at this point, and we're willing to pass it forward to the next cell. But at this point, we also want to generate the next hidden HT. Okay, so we're going to take it, pass it through element-wise tanh operation. So why are we doing element-wise tanh operation? It's just to squish the numbers. If the numbers are between, let's say, -100, +100, and all that, if you pass it through a tanh operation, they're going to be numbers between -1 and +1. So just like kind of bringing them into a range. And then we are using one more gate. Gate is exactly like the same thing, sigmoid with the same input, HT -1 xt, element-wise amplification with whatever is the tanh transformed cell state. Okay, tanh transformed cell state is here. Element-wise multiplication to amplify or de-amplify or turn something to 0, and then that's exactly is defined as HT. So it's passed as potentially for use for creating output scores, or pass it to the next layer. Okay, that's all. That's what's going on here. So I mean, there's a lot of moving parts, like a couple of 3 gates going on in addition to the original new information creation. But the important thing is the cell state, and hopefully the cell state is modified appropriately so that it can retain long range information. Okay? And empirically, it seems to perform better than the vanilla RNN for this situation. For wherever you see vanilla RNN, if you replace LSTM, it kind of performs empirically better. Okay? So I guess this is the final, just a recap. So there is this creation of what information to forget, what information to remember, remembered information adding to the cell state, and removing information which is forgetting, and then the cell state itself is being tarnished, and then some information is being removed from it, and then that's becoming HT. Okay, that's what's going on. Any questions about this?
So the previous target is the activation, it's the activation function, and the other one is just to.
Yes. This tanh is element-wise operation. I mean, this should ideally be a circle, but because we want to write tanh, so they made it a.
So this activation function would change, but the tanh would remain.
Oh, here tanh choice you can change it to relu or anything like that. This one also you can change, but then it will not be the original LSTM. It will be your variation of the LSTM. I think the one implemented in PyTorch. Actually, let's see. Oh yeah, this is just RNN. Actually, let me see if there's an LSTM link here. Okay, I don't see the LSTM version. Layers. So I mean, if you really think of like the matrix vector multiplication and all that, they by default, I guess you're using tanh there, and also tanh to modify the cell state. But I think you can actually potentially change it. So sometimes I don't know if they have a choice to change it. No, I don't see. Yeah, I don't see a way to change it. Yeah, so they don't have an option here, but sometimes they do. For example, for the vanilla RNN, they have an option like NN.RNN. They have an option to change the nonlinearity. Oh. What? That is surprising. Let's actually log in. Give me a second. Oh, it's saying it's in progress, but I can't log in. I can't join. Join. Okay. Okay. Let's figure it out. Okay. So interesting. Okay, remote folks, you can hear me, right?
Yes.
Let's drop these. What I was trying to show was that RNN has a choice of nonlinearity where you can change the Tanish to ReLU. Okay, so your question. So we can change Tanish to ReLU in RNN, but in LSTM implementation they don't have that choice. But anyway, let's come back to notation. Any other questions about this? So by the way, don't be afraid to open the documentation and read. I mean, sometimes function signatures are so generalized, so much battle tested that there may be so many options. Generally, you'll be using one or two options generally, but it's good to see what other options are there. Sometimes there's also a description of what's going on. Okay, so I will skip other variations. I mean, this slide is talking about something called gated recurrent unit, which is also quite popular. In fact, if you look at the LSTM, so if you just look at recurrent networks, recurrent layers, sorry, you can see GRU is also there, and basically RNN, LSTM, and GRU, and we have seen RNN and LSTM here. These implementations, just to note, these implementations do automatically the multiple calls to your green cells. Okay, so although in the lecture we've been talking about the green cell only, if you only want to look at the cell, then it's this cell versions. Okay, but generally you will see that people call NN.LSTM directly, and so that when you call that, if you have a sequence on 5, it will call it will do the 5-step operation for you. Okay, internally itself, it will pass the HT-1 to HT and all that. It will do it automatically. So just see an example, you get a sense of like what's the difference between this is not the green cell, but this is the full 5 times call or 10 times call of the green cells, depending on the sequence length. Okay. Yeah, as I was saying, don't be afraid to look at documentation. So let's come back. Okay, so we'll not spend much time on this, but just wanted to have a couple of comments before we pause for today. Is that there could be other variations to stack up these green cell boxes. I mean, they're just functions, right? Just like we could stack up fully connected layers like in any way, or con layers and all sorts of combinations there. Similarly, here you could stack up things like this. So where the output is output at the first level of RNN sequence, the HTs are basically then just redefined to be XTs for the next layer or next block of RNN module. Okay, so this is just stacking. This just increases the richness with which function data flows from while trying to make prediction, right? So people have done all sorts of stacking like this. But in general, the ones that are implemented, for example, in the packages like PyTorch or MXNet or TensorFlow, for example, GRU and LSTM, those are there only because they are empirically like the popular ones and the ones that are kind of really well validated in the real world. Okay, if you make your own version of things, then there has to be some good justifications, good experimentation to support in your domain, in your use case, a new cell architecture, and something like that may make sense. Okay. Yeah, and so training is exactly same. So we saw it with the character language model. It was just a appropriate cross entropy loss and backdrop just like before. If you want to really look at LSTM definition from like a dimensionality perspective, so far we've been using single arrows. But if you really want to know like how the dimensions deal, like how do concatenation and splitting happen, this slide just shows you for the two when the case when the xt is two-dimensional and ht is two-dimensional. So you can see that, you know, like for example, the tarnished layers needs 4 inputs because xt is two-dimensional and xt is two-dimensional and ht is two-dimensional. So any questions about this part, because I don't want to start the new part today, but no questions?
Parts train
This one?
like this, like they depend on each other or they're trained independently from each other? Like they
Oh, these 4 parameters, the parameters for the gates, the 3 gates, and there's parameters for tarnish, they're all trained together. Yeah.
together. Okay.
Yeah. So generally, when you instantiate something like this, right? So if you so nn.lstm, right? So let's say nn.rnn, it shows you here, like this is how you instantiate an RNN block, okay? And let's say you do from that, so that's like a block, and you give an input and produce an output, okay? So you do it for many examples, and then you compute loss. When you backdrop, all the parameters of the RNN block will get updated. Okay, so the same. So but the backdrop part is the same as before. So whatever we were doing, yeah, I think I closed that part. But whatever we were doing before, loss.backward and optimize other step is exactly the same. Yeah, and so you will get trained. So maybe maybe because you're seeing PyTorch only here, not you haven't seen that in assignment 1. But assignment 2 is making you lead up to and actually work with a fully concrete PyTorch script. I mean, that's why I'm strongly suggesting you look at the CNN example, get a feel for the cells, because the RNN examples will be very similar. Okay, almost the same template, almost the same training loop, except the model definition will be different. Okay, the model definition may involve nn.rnn instead of nn.linear. Okay, that's all. So of course, the challenge generally lies in like ensuring that the input dimensions, output dimensions match and things like that. But so yeah, so next time, just to give you a sense, like what's remaining in this deck is some examples. Next time, what we're going to do is talk about what is called attention. Okay, so I think I mentioned briefly some attention. There's something called encoder decoder attention. So we'll talk about what is encoder, what is decoder next time. It's just RNN cells. Okay, just some RNN cells are called encoder, some RNN cells are called decoder. That's fine. But there's a notion of attention that is new. We'll talk about that, and then we'll talk about what is called self-attention. Okay, self-attention is a core idea in transformer architectures. Okay, so next time, just to kind of give a teaser that next time we'll come back to NLP land. We are still in NLP land, even with sequences. The whole machine translation is a great example of sequence modeling. So next time we'll talk about encoder decoder attention, or attention that can be used with LSTMs. And then we'll talk about attention, which is self-attention, which is a core component of transformers. Okay, and all these models are still to be used for sequence-to-sequence models, sequence settings. Okay, and we'll see examples again next time. Most canonical example is translation. Okay? If you want to keep that at the back of your mind, but translation is not the only thing. You can always do many other input-output mappings. Okay, then we'll end it for today.
If I want to find an example for the LSTM model,
Okay, one second.